In Chapter 3, Cluster 2, we're going to be looking at logarithmic functions. Our first objective is to define a logarithm. Then we're going to write exponential statements in logarithmic form, and vice versa, write logarithmic statements in exponential form. And we're going to determine a log and natural log values using a calculator, or decimals in our case. All right. In this first situation, we're talking about spheres, and the volume of a sphere might be something that we would want to compute, or surface area. So there's two different formulas here. We're not actually going to use those formulas right now, but what we're thinking about is that both of those formulas involve the radius r, and so we want to think about spheres of various radii. So there's a box down here with the diameter of some spheres. So the diameter is just twice the radius, so we could get the radius easily if we had the diameter of the sphere. Anyway, noticing that these spheres, there are three spheres that have relatively similar diameters. Now, you might not consider a golf ball and a basketball to be of similar size, but when you're comparing those to the moon, the earth, and the Jupiter, you can see that the first three are similar in comparison with the other three. So we're going to graph these on these tables down here. Plot the first three rows on this table, starting at 0 and incrementing by 0.2. So 0.2, 0.4. I'm not going to label every one because I can't fit 0.6 and so on, but I'll go for 0.08. This one would be 0.1, then 0.12, then 0.14, 0.16, 0.18, 0.2, 0.22, and 0.24. So got a mismatch of the ones I've labeled just for space. I skipped a couple. So I've labeled, I'll mark off the ones I've labeled just to hopefully help identify them. If you have room to label them all, go ahead. All right, so I'm going to plot each of our points. So I'm going to use the different colors so my labels don't blend in with it. So the first one, the golf ball, 0.43. So this is 0.6. So 0.5 would be halfway in between. So 0.43 is going to be closer to the 0.4, not quite to the halfway mark there. 0.075. Here's 8. So this would be 7. 7.5 would be like 3/4 of the way between 6 and 8, or halfway between the middle and the 0.8. And then 0.239, that's going to be very, very close to the 0.24. So if you're thinking about these two items, the golf ball and the baseball are much closer in size than the basketball, so it's much further away in comparison to the other two objects. Okay, so can we plot the other three items on the same axis? So if I was to extend this and make it longer, maybe make it another page attached to it, could I fit these on? And no, because I would need to go for miles on paper. They're way too big, right? So no, because they are way too large for that scale. Okay. Now we're going to plot on the bottom of our page here the moon, the earth, Jupiter, and so on. So we're going to start our scale again at 0, and we're going to increment by 10 million meters. So I'm going to let my units here be millions, so I can just write 10 million, 20 million, 30 million, 40 million, 50 million, with not having to write all the zeros, just because that would be a pain. This is going to be 100 million, 110 million, and so on. And this last one is going to be 160 million. Okay, so now we again will plot on this scale the moon. So the moon is only 3 million. So if this is 0 and that's 10 million, then halfway would be 5. So I'm a little under halfway. Just an estimate like that for our moon. The earth, 12 million. So halfway is 15. So 12 million, a little bit bigger than the 10. And Jupiter, 142 million. So we've got 140, 145. So it would be in the middle. So 142, almost 143 million, somewhere over there. So similar to the previous, the moon and Earth are similar in size in comparison to Jupiter, which is way far out. Like the baseball and the golf ball were not the same size. We know that a golf ball is quite a bit smaller than a baseball, but when you compare them both to a basketball, they're both could fit in the palm of your hand, whereas the basketball is much bigger. These are both sizably comparable, and then Jupiter is a lot bigger. All right, on to the next page. Can we plot the other three, the balls, on the same axis? And the answer would be no. I'll flip back just for a second. Sorry, I was moving pages. But there's no way I could plot those three balls and have them distinct. They would be so close to zero that they would be on top of each other and they would look like they were zero. So there's no way that they would be able to plot and be distinct objects. And that's because they are too small in comparison. So they're too small for that scale. Okay, so then we think about their, oops, dropped my pen. Okay, so then we think about the scale, since we said they're too small for this scale. So what if we used a different scale? And so we're going to use a logarithmic scale to look at this. And for the logarithmic scale, we're going to use powers of 10 to delimitate the scale. So we'll have 10 to the negative 2, 10 to the negative 1. They want to just label these first of all. So this one would be 10 to the 0, 10 to the first, 10 to the second, 10 to the third, and so on. It's almost 16, 10 to the sixth, 10 to the seventh, 10 to the eighth, and 10 to the ninth. Okay. Now, in order to be able to graph on the logarithmic scale, I can put these numbers into scientific notation. So we'll do that. This one is going to be 4.3 times 10 to the negative 2. Then this one would be 7.5 times 10 to the negative 2. This one would be 2.39 times 10 to the negative 1. And then this one would be 3.476 times 10 to the 6th. Then 1.2756 times 10 to the 7th. And 1.42984 times 10 to the 8th. Okay, so if I graph these on my logarithmic scale, a logarithmic scale is, they're not equally spaced. They are spaced equally on power, but not by amount. So the gap between 10 to the 0, which is 1, and 10 to the 1, which is 9, is a gap of 9 digits. Then the gap between 10 and 10 to the second power, which is 100, is 90 digits. Then this is this is 100 to 1000, so 900 digits. So they're not equally spaced in terms of size, but they are equally spaced in terms of exponent. So we're going to place each of these numbers based on its exponent in scientific notation. So for the first one, 4.3, I'm not quite to halfway in between the 10 to the negative 2 gap and the 10 to the negative 1 gap at 4.3. If I was exactly halfway, I'd be at 5 in the 10 to the negative 2 gap. 7.5 then 10 to the negative 2 gap. That one's going to be 3/4 of the way or so. So we'll put those 2 dots there for the golf ball and the baseball. Then our basketball is at 2.39 in the 10 to the negative 1 gap. Then our moon is at 3.4 in the 10 to the 6th gap. And Earth is at 1.2 in the 10 to the 7th gap. And Jupiter is at 1.4 in the 10 to the 8th gap. Okay. So this allowed us to graph all 6 of the objects on the same scale, on this logarithmic scale. What we can see here is that these 3 objects are certainly a whole lot smaller than the latter 3 objects. The balls are smaller than the planets and moon. You can also see a little bit about the size differential between these because they are jumping up by a power of 10. So in the previous scale, I couldn't really tell that the Earth was a lot bigger than the Moon because they were both so far down towards each other, and Jupiter was so far spread out towards the other. But here I can see that the Earth is a magnitude larger in order than the Moon. So I get even more information from this about the planets than I did with the large scale. The large scale was too big to really think about those two together. I could just see they were similar in size in comparison to Jupiter, only because Jupiter was so much larger. All right. So the scale we use is a logarithmic scale. Um, and sometimes on a logarithmic scale, we just label the powers of 10. Like, so I might just label this as exp to -2, exp -1, just as a power of 10 as well. So we're going to rewrite that with the powers, just the exponents of 10. Okay, so this is our 10 to the n scale, and so we'll have the powers of 10. I don't know if I missed anything there. I don't think so, but I have more space than I did in the last ones for some reason. So I can graph my 2 dots here that I had before. I can graph this dot here. I can graph the dots for the 3 planets up here. And again, sometimes we just will list the powers, knowing that we're in a logarithmic scale. We won't write the whole 10 to the stuff just to save space. We'll just write the exponents on the notation. And I just put the dots in the same positions they were in the previous gaps. Okay. This axis, though, could be misleading because it looks like a standard axis, but it's not, because these are not incrementing by 1. They're incrementing by a power of 10. Okay, so focus on values between consecutive tick marks. So if you're in a regular scale, the distance between, say, 2 and 3 is 1, but on a log scale, the distance would be 10 to the third minus 10 to the second, which is 900. So there's a lot of, again, I was just picking this one to talk about. The amount of space between those 2 points is not 1, it's 900. And they're not equal. So if I picked another gap, like 0 and 1, it would have been 1 minus 0 is still 1 gap of space, but that's not what it means, because 10 to the first minus 10 to the 0 is 9, like we said before. So they're not equally spaced in terms of counting by digits, but they do allow us to see the picture in a different way. Okay, so that is a little bit about a log scale. We get the sense that logs are used to help us size a number, to see how large the magnitude is another word for the size of that number is. Okay, so the exponents used to label the tick marks are logarithms, or simply logs for short. Since these are based on a power of 10, they're logs base 10. Logs base 10 is the common log. So a common log has a base of 10. And so we actually just use LOG as the abbreviation for a common log. Okay. All right. So continuing down on the next page, the common log of a power of 10 is going to be equal to its exponent. So the log, determine the common log of each of the following. So the log of 10 to the negative 1 is going to be the exponent -1. The log of 10 to the 4 is going to be the exponent 4. The log of 1,000, 1,000 is the same thing as 10 to the third, so it's going to be the power 3. 100,000, that is 10 to the fifth, so its common log is going to be 5. And this is, let's see, 1, 2, 3, 4, 10 to the negative 4, so its log is going to be -4. Okay, now these haven't been written in proper notation. They have used the words to determine the common log of each of the following. So let's go ahead and get them into proper notation on the next page. And proper notation, actually on the bottom of the page, starts looking like this. If I wanted to ask you what the log of 10 to the third was, from the previous example, we said it was 3. The proper notation is going to ask me what the log base 10 of 10 to the third is, and then I'm going to say 3. So I'm going to put the log notation right into my question. Now, because it is a common log, the notation log base 10 is shortened to just log. We don't write the little tiny 10 in the common log. We just write log, and what we mean by log is a log with base of 10. If the base is not 10, if the base is 2 or 8, we'll have to write the base in. But if the base is 10, we're just going to abbreviate it, shorten it by dropping the 10. So the log of 10 to the negative 1 asks me the question, what power of 10, which is the base, is 10 to the negative 1? And so what power of 10 is 10 to the negative 1? It's the negative 1 power. So I get negative 1 as the answer. Since all of these have a base of 10, the answer to the logarithm is the exponent. The answer to any logarithm is the power the base needs to be raised to get the argument. So log of 10 to the fourth is fourth power. What power of 10 is 1,000? Third power. What power of 10 is 100,000? That's the fifth power. What power of 10 is a negative, 0.0001? That is the negative 4th power. These should match up to what we saw on the previous page, number 5. These are just now written, instead of in words, they're written in logarithmic form. So our answers should match those from the previous page, problem 5. All right. So we're going to keep looking at the bottom, and we're going to look at logarithms with other bases. So maybe the base of our logarithm is 4 or 2 or 3 or so on. Okay. So again, every time I see a logarithm like this, I am being asked a question about a power. So when I see the log base 4 of 64, this asks me what power of 4 is 64. Well, power of 4 is 64. Well, I know that if you raise 4 to the third power, you get 64. So the answer must be 3, because 4 to the third power gives me 64. What power of 4 is 64? The answer to a logarithm is the power that you need to raise the base 4 to get the argument 64. Okay? So in our statement up here, a statement in logarithmic form, log base b of x equals y. B is the base of the logarithm. The x is something that's a power of b, and y is the power itself. So the answer to the logarithm y is the power that you raise the base to get the argument x. All right, so let's look at another one. What power of 2, what is log base 2 of 16? So I'm going to write some things that I know about 2 up above. I know that 2 squared is 4. That's not going to be the right number. I know that 2 cubed is 8. That's not the right number either. And I know that 2 to the 4th is 16. I'm like, oh, that's close. So something about 2 to the 4th. 2 to the 4th is 16, though. It's not 1 over 16. So I need to think about exponents and what kind of exponent would give me a fraction. And so I know that if my exponent was negative, then it would move the argument into the denominator. So it would move the 2 to the 4th or the 16 into the denominator. So the answer to this one has to be negative 4. If I raised 2 to the negative 4 power, I'd get 1 over 16. So those are some of the thoughts that go through my head as I try to figure out what the log base 2 of 1/16 is. Negative 4. All right. Now, in the next one, log base 3 of 9. What power do you have to raise 3 to get 9? We probably could identify that one right away as 2, knowing that 3 squared is 9. If I think about number 3, number 2 was again, oops, I should have written the 3 squared first. 3 squared equals 9, and so I knew that the power on 3 was going to be 2. And if I keep thinking about 3, 3 to the third is 27, so it's a fraction again. I know that if I had 3 to the negative third, that would give me 1 over 27. So my answer is going to be negative 3 for this one here. All right. So in general, this property of logs, the log base b of b to the n is n. Again, what they're saying is the log base b of b to the n is n. What power of b is b to the n? The answer is the power on your base, right? The answer to a logarithm question is the power that you need to raise the base to to get the argument. All right. Now, sometimes these logarithms get to be a little complicated, especially if you don't have a big familiarity with your exponents and don't know what 2 to the 16th is. Maybe we need some assistance with some of those. So let's take a look at decimals for a moment. And I'm going to look at the top of the page first. And just want to note that in my decimals area, I can type in log of 10 to the -1, just like it was printed up here for number A, and it's going to tell me it's -1. And I'm just going to skip down to D. I could do log of 100,000. I have the right amount of zeros there now, and it's going to say it's 5. And I could do log of 0.001. I must have missed a 0. That's correct, right? There's 3 zeros and the 1, and I get the -4. So I can type those ones just like that, and they do compute the answer. So it's completely possible to get some assistance with these, but I want to get some familiarity with where these numbers come from as well. So having both of those things will be extremely helpful. Now, when you type in just log, the base of this is assumed to be 10. So I can't do plain log for any base but 10. Now I'm going to use the underscore key. So if I go into notes and type it like that underscore key, that's going to lower a number to the bottom corner of my log. So in the previous one, I can do log, hit the underscore key, see how it pops my mouse down there? Then I can do log base 10, and I'm going to go over of 0.001. And again, I get -4. So it doesn't matter how I enter the common log. I can enter the base explicitly as 10, or otherwise it's assumed to be 10. All right. Now I'm going to do the same thing for this bottom set. Let's evaluate these ones. But this time I'm going to have to explicitly state what the base is. So we're going to do log, and we're going to do underscore to explicitly put that base in, log base 4, over, and then of 64, it's 3. Now, if you prefer using the keypad instead of the underscore key to drop your power or your subscript, your base down there, you can. So if you go into functions down towards the bottom, I think I passed it. There's a log base. I don't know why it's in the calculus area. It's not really calculus, but that's where I found it. It might be in miscellaneous as well. Nope. So there it is. So I can do the log base and click on this button, and it has my mouse pop into the underscore area. I can just type the 4 in the base and then my 64 in my argument, and I still get the same thing. I prefer typing the underscore because then I have less stuff to do, less stuff to click around and try to find. Okay, so I'm going to type my next one. Log underscore base is 2 of, now this time I went to do 1/16, and I noticed that my division went underneath everything, so I can't do that, but I have to go put in some parentheses to do my 1/16, and then I can get my -4. So I want to watch and make sure that I have the entire number inside the logarithm, so parentheses may be necessary. When I clicked on the function, notice how they gave them to me automatically. They're not necessary if I have a single term inside the logarithm. However, if I have something that's a component expression like a fraction, then I'm going to need to insert them myself. So log base 3 over of 9, that was 2. And then last one, log base 3 of 1/27, that was -3. So all of these can be checked, like I was saying, in decimals, but I do want you to understand where these values are coming from also, because we're not always going to be plugging numbers as our arguments to logarithms. We're going to have variables also, and so we want to make sure that we have an understanding of what these logarithms mean for us. All right, on to the next page. Some properties of logarithms. Okay, the log of 1. Now, because there is no visible subscript, it's got to be 10. That's the only invisible subscript on a log, on an LOG log. So my base is 10. So this is asking me what power of 10 is 1. And I know that if I raise 10 to the 0 power, I get 1. And so the power is 0. So the answer to this one is 0, because 10 to the 0 power would give me 1. So the log of 1 is 0. Then they asked me what log base 5 of 1 is. And I also know that 5 to the 0 power would give me 1. So this is going to be 0 as well. What about log base 1/2 of 1? What would you have to raise 1/2 to get 1? Still 0, because anything raised to the 0 power gives me 1. Okay, so in general, the top line right here is it doesn't matter what the base is. Log base b of 1, no matter what b is going to be 0. Because if you raise b, the base, to the 0 power, you'll get 1 as the argument. So the power that you need to raise the base to get 1 is going to be 0. The answer to the logarithm is the power that you would need to raise the base to get the argument. Okay, then the next row. Okay, the part D here is, again, an invisible base. The base is 10. So they're asking me what power of 10 is 10. And I know that 10 to the first power is 10. So 10 to the first power of 10, I would need to raise 10 to the 1 to get 10. So my answer is 1. That's the power I would need to raise 10 to get 10. What power of 5 is 5? Log base 5 of 5, that's also 1, right? You have to raise 5 to the first power to get 5. What power of 1/2 is 1/2? What's log base 1/2 of 1/2? I have to raise 1/2 to the first power to get 1/2. So another general rule here is that log base b of b is going to be 1. You would have to raise the base b to the first power to get b itself. So the answer is 1 as the first power. Okay. These two rules are outlined in this properties box here. In general, log base b of 1 is 0, and log base b of b is 1, with, of course, the caveats that b has to be a non-zero number and it can't be 1 because the base of an exponential function can't be 1, and neither can the base of a logarithmic function. All right. Now, on to the natural logarithms. Okay, so the base can be any number. We've seen bases of 10, of 1/2, of 5. Another common number that comes up in our exponential functions is the base e. That was the base for the compound continuous. And most things are probably going to grow continuously. So it's a pretty natural number. It is going to be common in most growth or decay cases. Because it is so frequent, we can't use the word common for it because the common logarithm is already taken with the base of 10. We're going to use natural log for the base of e. Natural log has a base of e, and the shorthand for log base e is ln x. We read the letters ln, like the letter L, the letter N, to say the shorthand for the natural log of x. You can also read that as natural log. It can be read as natural log or ln x. Okay, so the natural log is a logarithm with a base of e. So if I am looking at question A down here, what is the natural log of e to the 7th? That asks me what power of my base, the base of the natural log is going to be e, is e to the 7th. Well, e to the 7th is the 7th power of e. So my answer is 7. All right. In the next one, natural log of 1 over e to the 3rd. They're asking me again, what power on e is 1 over e to the 3rd? And so I'd have to think to myself that, oh yeah, if I had e to the negative 3rd, that would have made 1 over e to the 3rd, right? Negative power would have moved it into the denominator. So the power on e on this one had to have been -3, because it not only was the power on e, but it was in the denominator, so that negative pushed it down there. Okay, what power on e? What is natural log of 1? What power on e gives me 1? I already know that the 0th power of anything gives me 1, so it's going to have to be e to the 0th power. Natural log of e. What power of e is e? E is e to the 1st power. And the natural log of the square root of e. What power of e is the same thing as the square root of e? Well, I know from chapter 2 that fractional powers are the same thing as square roots. So the answer is going to be e to the 1/2 power. The 1/2 power would be the same thing as the square root. So I have e to the 1/2 is the same thing as the square root of e. So the natural log of the square root of e is 1/2. All right. Now, again, we talked about how we know each of those from what we know about powers on e. Natural log can just be typed in with the letters L and N. So I can do ln of e to the 7th, that's 7. I can do natural log of 1 over e to the 3rd, it's -3. Put my parentheses in the wrong spot, but that's okay. And then I can do natural log of 1, natural log of e, and natural log of the square root of e. Ooh, I have to put parentheses because it's freaking out about the square root order of operations there. And there I get, with the parentheses, my 1/2. Okay. So again, they can all be entered because there's no variables in here. This is all numeric. So they can be entered into decimals for confirmation, just to make us feel good. But we can figure them out by identifying the answer to the logarithm as a power on the base. All right, and bottom of the page, we have the equivalency here, that something of the form y equals log base b of x is equivalent to b to the y equals x. So the base is b in the logarithmic situation. The base is b in the exponential situation. So the base stays the same. The answer to the logarithm, y, is the power that you would raise the base to get the argument x. So these two are equivalent. So we're going to be switching things from their logarithmic form to their exponential form and vice versa. All right, so I'm going to make a note of that again right here. B to the y equals x is equivalent, that's a symbol for equivalent, just a double line and 2 arrows there, to log base b of x equals y. On the top line, we have some things that are already in logarithmic form. We're going to switch from logarithmic form back to exponential form. Then the bottom, we have things that are already in exponential form. We're going to switch them into logarithmic form. All right. So to go from logarithmic form to exponential form, first of all, the base is 2 on this logarithm. So the base is going to be 2 of the exponential. The power y is the solution to the logarithm. So 2 to the 3rd equals the argument 8. Now, you know this is true. 2 to the 3rd is equal to 8. This is also true. These two sentences, these two mathematical sentences, tell me the same information, just in a different order. 3 is equal to log base 2 of x. The power you have to raise 2 to get 8 is 3. Right? They tell you the same information. You're not solving anything, you're not doing anything, but you're rewriting a sentence from logarithmic form to exponential form. Okay? They're both true sentences. Let's do it again. What's the base? Now the base on this one is invisible. It's not shown here. It's not the e that you see here. That e is part of the argument. Natural log has an invisible base. There's no subscript visible. It's e. Okay? So the e that I'm going to use first is an invisible e. It's not shown because natural log is the shortcut for log base e. Okay? The power on this e is 3. And this is equal to the argument, which is e to the 3. And again, obvious that that is true. E to the 3 is e to the 3. Yup. It's a little easier for us to read exponential notation still than it is to read logarithmic notation, but this is also very true. What power on e is e to the 3? The 3rd power. So again, very true in its original form. Okay. All right. 2 is the base. To the -4 equals 1 over 16. So we've gone from logarithmic form to exponential form. And again, that one should ring out as true as well. Now, the next 3, we're going to go opposite. They're already in their exponential form. So we're going to write the logarithmic form. 6 to the 3rd is 216. True fact. So if I switch this into logarithmic form, I'd be saying log base 6 of 216 is 3. Again, true fact. What power did you raise 6 to get 216? The power is 3. Now, the base of this logarithm is going to be e. So I would not write this. I'll write it real quick, but I would not write this as log base e. I could. It's just a little sloppy to write that as log base e. Then of the argument is e equals 1. What we want instead here is to shorthand this log base e to natural log of e equals 1. Natural log is a log with a base of e. Okay, and then over here, the log base 3 of 1/9 is equal to -2. Okay, so all the logarithms that we've done previously have been logs that we can do by hand. What we're going to look at next is logs and the calculator. These are some logarithms that cannot be done by hand because the arguments are not powers of the base. This was asking me, what power of 10 is 20? Well, 10 to the first is 10, 10 to the second is 100, 20 is not on the list of things you can do, but the calculator can give us an approximation for it. So we will do some of these by approximation. They want us to do the log of 20. Well, it's approximately, oops, I don't know what I was trying to write there, approximately 1.3013. I'm going to keep a couple places on this because I wanted to check it. This is supposed to be the power that I raised 10 to get 20. So I said 1.301013. And there were some more places. I could have kept a little bit more accuracy. But yeah, you can see we're basically getting 20, even if I had rounded it to 5 places, right? So I should be getting 20. If I kept the whole number, I might get even closer to 20. Let's see. I can't copy. Can I copy? Nope. There we go. There we go. And again, I'm not quite to 20 because this last digit is rounded as well. So whatever, if I got some more precision, I might be able to get exactly 20. But again, it's really, really close to 20. So maybe there was a digit after it that was like a 4 or something. I don't know what comes next. I guess a little lucky there. So there's probably more digits after that as well, but we're getting close. All right. So the next one, natural log of 15. Okay. 2.70805. Natural log of 1/2. Now it's a fraction as the argument. You would expect the power to be negative, so that's good. Negative 0.69315. And the log of 0.2. It's smaller than 1, so another negative. I didn't put an extra 0 in there. There we go. So now it's negative 1.69897 and some change. Okay. Now, what we're going to do now is when we did our ball analysis before and we graphed these things, we had previously graphed using just the exponent as a size for scientific notation. Now we're going to use the log of the diameter. We're going to see how those compare. Okay, so the log of 0.043. So this is negative 1.367. And log of 0.075, negative 1.125, then log of 0.239, negative 0.622. Then I have log of 3,476,000, and I have 6.541. Oops, can't type. It wasn't looking. I missed my O. There we go. 12,756,000. 7.106, and the last one, log of 142,984,000. 8.155. Okay, so graph these dots on the scale. So again, this is my powers of 10. This is my logarithmic scale here. Actually, no, this is regular digits. This is regular digits, but they do mean powers of 10. So I'm going to graph these numbers on this scale. It is a logarithmic scale, but I'm going to graph negative 1.3, negative 1.2, or 1, 2. Those are probably really close to the negative one side. Negative 0.6, then 6.5, 7.1, 8.1. Compare the preceding with the log scale in 3 and comment. Okay. I have to move this out of the way. There we go. So we are comparing over here with those 3 balls and these 3. It's similar. There's a little difference on these ones because I don't think I was, I think I was a little closer to the 10 to the negative 2 on this one. And here I'm a little closer to the negative 1 based on these numbers. So this one is the more accurate way to deal with it because the whole number, not just the size, has been used for placing. The other one got us in the ballpark, but the true logarithm of the value has gotten us the item graphed in logarithmic scale. So we'll say that they are similar, but we're going to go with this one as more accurate.